Okay, so we're going to be looking at how to apply the chain rule. Now let's take a look at what the formula is first, and then we will do some examples after that. Okay, so the formula, if you have a composite function f of g of x, and you want to find the derivative of a composite function, when you have two functions composed with each other, you're going to use the you're going to differentiate twice, which basically involves a chain of differentiation. Okay, so here, if you want to differentiate this entire expression, so f of g of x, let's put this prime, the derivative is going to be the derivative of the outer function f prime evaluated at the inner function multiplied by the derivative of the inner function evaluated at x, g prime of x. Okay, so this is the chain rule. It's a chain because you're differentiating multiple times within one problem. Alright, so a visual way to look at the derivative, let's say you are looking at so visual way, you want to look for d dx of outer function f of g of x. You have only two functions here, so you're going to be differentiating twice. Okay, so what you do with a setup like this, if we want to do this visually, is you take out the outer function. The outer function is f of x. So you take out the outer function, and then you look for its derivative. Okay, so the outer function as a simple function, not composite, you take it out and look for the derivative, and then you extract your inner function, which is g of x, and then you look for its derivative. Okay, so you have the outer function, its derivative, the inner function, its derivative, and then you put them together using the chain rule. So you have the outer function, the derivative of the outer function evaluated at the inner, which basically means you take the inner function and plug it into the derivative of the outer function. You plug it into the x. Alright? And then you multiply that by the derivative of the inner function. So your final result will be the derivative of the outer function evaluated at the inner times the derivative of the inner function. So one common mistake that students make is they differentiate the inner before they plug it in. You don't do that. When you're differentiating the outer, leave the inner alone, and then you multiply by the derivative of the inner. Okay? Alright, so for the examples, we are going to be finding the derivative of each function with respect to x. So find the derivative of each function with respect to x. Alright, so the first problem that we're dealing with is, let's say we have y equals cosine x to the fourth power. Okay, so now we're going to use the chain rule here. Why do we know that we have to use the chain rule? We have two functions composed with each other. The outer function is cosine x, and the inner function is x to the fourth. So what we're going to do is we're going to tear it apart. Let's take out the outer function. The outer function is f of x, which is cosine x, in its parent form. You don't write it as a composite. And then the inner function is g of x, which is this quartic monomial x to the fourth. So when you decompose the functions, what you do next is you will go ahead and differentiate. Okay? So the derivative of cosine, if you use your differentiation rules, remember when you're differentiating the c functions, you have a negative. So negative sine x is the derivative of cosine x, formula number 12. And then the derivative of x to the fourth, let's do a real quick review. So the derivative of x to the fourth, you power down the power, and then you mark it down by 1 for x to the third. Okay? So now we're going to use the chain rule. Derivative of the outer evaluated at the inner. So we're going to take the inner function and plug it into the derivative of the outer. And then we'll multiply our answer by the derivative of the inner. Okay? So dy dx is going to be, let's put the formula over here. Just to guide us. So the formula for write this properly. F of g of x prime is derivative of the outer f prime evaluated at the inner, g of x, times the derivative of the inner. Okay, so this piece, f prime evaluated at g of x, is basically negative sine x evaluated at x to the fourth. So we plug it in there, so that gives us, let me color code it so that you can see what's happening. Wrong color. Negative sine of x to the fourth. That is the derivative of the outer evaluated at the inner. Okay, times the derivative of the inner, which is 4x to the third. Let's make it look pretty. The derivative of y with respect to x. Now this is how you write functions. You write the polynomial function first before the trig function. That's the order, okay? Negative 4x to the third sine x to the fourth is your final answer. That's the refined form of the derivative of y. Okay? Okay, for number 2, what if we want to find dy dx, derivative of y with respect to x, of the arc cosine of 5x to the third. So the outer function is an inverse trig function composed with a polynomial function, this cubic monomial 5x to the third. So in order to use the chain rule, what we're going to do is we're going to decompose the function. Okay? So the outer function is going to be the inverse cosine. So f of x, let's call the outer function f of x. That's going to be the inverse or arc cosine of x. And then the inner function is this cubic monomial here. Let's call that g, which is 5x to the third. Okay? Okay, so let's put the steps on the side here so we don't get this confused. So first thing we do is we decompose, okay? And then after you decompose, you differentiate. We differentiate the components. Alright, that's what we are going to do next. So you find the derivative of f prime of x. So the derivative of the inverse cosine of x is negative 1 over the square root of 1 minus x squared. Okay? and then you differentiate the inner function g prime of x. Alright, so g prime of x is 15. You power down, but there's already a 5 there, so 5 times 3 is 15. X to the, you mark down the power by 1, 15x squared. Okay? So step 3, you use the formula to recompose. So the formula is basically, let me just write down the right side of the formula, f prime of the inner, derivative of the outer evaluated at the inner, times the derivative of the inner. Okay? So what's happening here is we already have the derivative of the outer, so we're going to take the inner and plug it into wherever you have an x. That's what composition is all about. And then multiply that result by the derivative of the inner. Okay? So y prime or dy dx is going to be this evaluated at that. We have negative 1 over the square root of 1 minus, instead of x squared, we have 5x cubed square. And then we'll multiply that by the derivative of the inner, which is 15x squared. Okay, we're going to go ahead and refine our result or simplify. So that's step 4. Refine and simplify. Alright, so what can be simplified here? If you take a look at the denominator, the radicand, in the denominator, we can raise 5x to the third to the 6th power. If we apply that rule, dy dx, and if you want to refine this, the numerators we can multiply with each other. So we have negative 15x squared times 1 is 15x squared. All that divided by the square root of 1 minus. Now, you got to be careful with this square here. You're squaring a product. So when you're squaring a product, you have to square the factors. You have to square the 5, and you have to square x to the third. Okay? So 5 squared is 25. X to the third square, when you're multiplying a power to a power, or when you raise a power to a power, you multiply the powers. So it's x to the 3 times 2, which is 6. Okay? And that right there is the denominator component. And this, ladies and gentlemen, is the final answer. For number 3, we want to find dy dx, where y is equal to e to the 4x squared. Alright, so let's go ahead and decompose the functions. The outer function here is f, let's call it f of x. That is e to the x. I'm going to go a little bit faster here since we're kind of getting a hang of it. The inner function is what x is plugged into in this parent function right here, which is 4x squared, the quadratic monomial. G of x is 4x squared. So we're going to apply step 2 of the steps. We're going to differentiate the components. So f prime of x, e to the x is its own derivative, e to the x, and then g prime of x, using the power rule, 2 times 4 is 8x. Okay? To finish this off, using the formula, you take the inner, plug it into the outer. So this is the derivative of the outer evaluated at the inner multiplied by the derivative of the inner. Alright, so our final answer, the y dx, is going to be e to the, instead of x, we plug in the inner function, 4x squared times the derivative of the inner, which is 8x. Now let's go ahead and refine our answer. So whenever you have an exponential function and a polynomial, the polynomial comes first, okay, as a product. So you have 8x e to the 4x squared. Ladies and gentlemen, that is your final answer. All right. Okay, so let's take a look at the last one. Question 4. So let's go a little bit faster here. So we have y equals the natural logarithm of 2x squared. Okay, this is a composite function of a natural logarithmic function and a polynomial function. Step 1, we decompose. So the outer function is ln x, and the inner function is the argument of the natural logarithmic function, which is 2x squared. Differentiate both of them. The derivative of ln x is 1 over x, and the derivative of 2x squared using the power rule is 4x. Now if we apply the chain rule, we're going to look at the derivative of the outer evaluated at the inner, basically taking the inner function and plugging it into all the x's of the outer, and then we multiply that by the derivative of the inner. Let's go ahead and finish this off. We're now going to apply the chain rule formula. dy dx is going to be derivative of the outer evaluated at the inner, 1 over, instead of x, we plug in g, 2x squared, times the derivative of the inner, which is 4x. What we're going to do now is we're going to refine and simplify, or simplify and refine. So let's see what we have here. dy dx is 4x over 2x squared. We can reduce this using the properties of exponents. 2 goes here 1, 2 goes here twice. When you're dividing exponents, you subtract the smaller power from the bigger one, and you keep the power at the bigger one. Okay? So basically, x to the 1, you subtract 1 from this one right here. So that's going to become 2 over x to the 1. Like that. So dy dx is equal to 2 over x. And ladies and gentlemen, that's your final answer. Okay?